the profiler in R is a really handy tool for when you're developing larger programs or doing really big data analyses. And you're essentially you're running R code that's taking a lot of time or longer than you want to wait. Of course, that's all relative depending on kind of what you're working on, and maybe there are other things that you can do while you're running a program. But if something's taking a long time, the profiler is a really handy tool to figure out exactly why it's taking so much time and how to and to suggest kind of strategies for fixing your problem. And so I'm going to talk a little bit about using the R profiler and kind of talking about when you might need to use it. There are also some other tools that I'll talk about that'll help you kind of time your programs and time your functions, and so the conjunction of the profiler with these other tools is a really handy toolbox for figuring out how to optimize your software. So the first question you want to ask yourself is, is your code actually running slowly? And sometimes you can solve this problem by just, running your program and then going and doing something else. But sometimes that's not an option, and you need your program to really run quickly. And so profiling is a systematic way to examine how much time is being spent in various parts of your program. And it's particularly useful when you're trying to optimize your code, when you're trying to squeeze, a lot of efficiency out of some code. And a lot of times when you first start writing code, it runs fine, when you're running it once, and maybe you're writing a small piece of a function or a small piece of a larger program, and it looks great when you're running it. It seems to run very quickly when you're doing it. But then sometimes these pieces get embedded in a much larger program, and maybe a larger program is running your piece 1,000 times or 5,000 times or even 10,000 times. And then your one little piece, which was running great when you were running it, is kind of slowing down everything else because it's being run 10,000 times. And so now you need to make it a lot faster because it's being iterated over a lot. And so profiling can come into play when, for example, if you have a piece of code that runs great, but then when it gets embedded in a larger piece, its speed becomes much more noticeable. So, in general, when it comes to optimizing your code, the general rule is that you shouldn't do it. And what I mean by that is that you shouldn't think about it at first. And the first thing that you should think about is kind of how to get the code to run, how to make it readable, how to make sure that other people can understand what you're doing. And one of the reasons is that it's often difficult to understand where exactly your program is spending all of its time. And in order for you to speed up your program, you need to be able to know where it's spending its time. And so this can't be done without any kind of, it's difficult to do this, I should say, without any formal performance analysis or profiling. And so the basic idea is that you should always design your code first and make it so it's understandable, and then after you've got something working, then try to optimize it. And then the famous phrase is, premature optimization is the root of all evil. If you try to optimize first, the chances are that you'll introduce bugs before you even get a chance to kind of get things working in the first place. Once you've decided that you want to optimize your code, though, you should, act like a scientist, just like you would in any other context. You should collect some data, right? So if you have a sense of where your program is kind of being bogged down or where it's spending all its time, you should collect the data to figure it out. And the way that you collect the data is by profiling. So the first tool I'm going to talk about is actually not the profiler. It's a very simple function called system.time in R. And what system.time does is it takes an arbitrary R expression and it evaluates that expression and then tells you the amount of time it took to evaluate that expression. Now this expression could be very simple, like a single function call, or it could be very complicated if it happens to be wrapped in curly braces. So it could be actually a very long expression if you want it to be. So the basic idea is that you take this expression and it gives you the time in seconds that was needed to execute the expression. If there's an error in the code while the expression is being evaluated, then you'll get the time until the error occurred. Now, there's two very important notions of time when you're executing an expression on the computer. The first is called the user time, and this is the amount of time that's charged to the CPU or CPUs for running this expression. Okay, so this is the kind of time that the computer experiences. roughly speaking. The elapsed time is sometimes called the wall clock time, and this is the amount of time that you experience. All right, so so even though you're the user, you're not the user time. You experience the elapsed time. And so the two different notions of time can have kind of different importance depending on what you care about. So usually the user time and the elapsed time are relatively close because the amount of time that the computer spends to executing your function or your expression is roughly equal to the amount of time that you spend waiting for it, right? These are for standard kind of computing types of tasks. However, there are times when the elapsed time will be greater than the user time, and there will be times when the elapsed time is smaller than the user time. So the elapsed time can be greater than the user time, so that means that you spend kind of more time waiting around than the computer actually spent dealing with your code. And the idea is that the computer may spend a lot of time waiting around for other things to happen, things that are maybe external to the program itself. And so the CPU doesn't actually spend a lot of time working on your code. It may be spending a lot of time working on other things that are going on in the background. If the elapsed time is smaller than the user time, this most commonly occurs if your machine has multiple cores or processor and is capable of exploiting them. And so most computers these days have at least 2 or 4 cores or multi-core machines, and so this is a very common situation. However, it's not always that the program that you're running will be able to kind of exploit the use of multiple cores. In particular, the basic R program does not use multiple cores as of yet. However, it often links to libraries that do use multiple cores, and the most common one will be a linear algebra type of library. So if you're doing something like regression or a lot of these prediction routines or matrix computations, these all involve linear algebra libraries. And many of these libraries have been optimized to use multiple cores, and so they're called multi-threaded BLAST libraries, or for the basic linear algebra standard libraries, subroutines libraries. And on the Mac, sometimes called veclib or accelerate. There are more general libraries like Atlas. For AMD machines, there's ACML or ACML, and for Intel machines, there's MKL. There's also parallel processing libraries. For example, the parallel package, which can use multiple cores, but it can also use multiple computers. And so this will potentially lead to a program that takes more user time than it does elapsed time. And I'll give an example of how this will work. So one example of when the elapsed time will be bigger than the user time is if you read something from the web. So here I'm just using the read lines function to read a web page off a remote server, and you can see that the elapsed time is about 0.4 seconds, but the user time is 0.004 seconds. So the CPU actually doesn't spend a lot of time running this code because the chunk of the time is just spent waiting for the data to kind of go over the network and to come back to your computer. And so waiting for the network to kind of deal with the data going there and coming back is not really part of your program. It's part of a different thing that the computer is doing. And so the amount of time executing your program, in this case just the read lines function, is relatively small. In the second example, this is where the elapsed time is less than the user time. I've created a simple function which creates a Hilbert type matrix, and I calculate the singular value decomposition of this matrix with the SVD. So the SVD function makes use of the accelerate framework on the Mac, which is a multi-threaded linear algebra library, and so it can take advantage of the 2 different cores of this computer that I'm using. And so you can see that the user time was roughly almost double of the elapsed time. So the elapsed time was about 0.7 seconds, and the user's time was about 1.6 seconds. And the reason is because the underlying linear algebra library split the computation across the 2 cores, and so you can think of it as that basically the elapsed time was multiplied times 2 because it was being executed on 2 different CPUs. So the amount of time that the CPU spent working on your program was actually more than the amount of time that you spent waiting for it to come back. You can time longer expressions by just wrapping everything in a set of curly braces. So here I've got a for loop here that's just generating some random normal variables, and you can wrap that whole thing in curly braces and call system.time around it. And you can see that here this is a very simple expression. It's not multi-threaded. There's no network activity. And so the user time and the elapsed time are basically the same. So the system time is a really handy function if you just want to take a little piece of code, figure out how long it takes to run it, and kind of go through a program, maybe expression by expression or line by line, to see which parts are taking a lot of time. Now, the part of the problem with system time is that it assumes that you know where to look. It assumes that you know where the problem is and that you can call system time on a given expression. And so this may be useful for smaller programs, for less complicated programs where you have a very good sense of kind of where the bottlenecks are. But the question is, what if you don't know where to start? What if you don't know where the problems might be and where to start looking? And so you need another function to kind of help you along with that.